Hi guys, so today in this video I'm going to be talking about spatial partitioning. And what spatial partitioning is basically a design pattern when designing a game. And in this case, it's a way to improve the performance of games that uses a lot of different objects. So the scenario I'm going to use today, just to give you a better understanding, is imagine soldiers on a battlefield. Whenever they're on the battlefield, they need to always check where each other are. So when to swing their swords and what to do, etc. So what you see on the screen, this is basically your space, your world, the battlefield. And what I've done is I've split it up into these little cells as a grid. So this is basically spatial partitioning here. So the space is the world and the partitioning is splitting it up into these little cells. So what I'm going to do now is just put in a couple of circles just to represent some soldiers on a battlefield. So I'll put one there and one there. I'll put that one red. Perfect. So what they're doing now on the battlefield, they're constantly basically searching for each other on the battlefield, and it's using a lot of resources. And if you have hundreds of these soldiers on the battlefield, it's going to be terrible. You're going to use too many resources, and it's not going to be good at all. So this is when spatial partitioning comes in. So instead of constantly searching the entire space for one another, you're only going to be searching for each other within each individual cell here. So this blue circle, for example, as it moves across, it's only going to search for the other object within its cell. So as they both get closer to each other, and they both end up in the same cell, then they're both going to detect each other and obviously do whatever you program them to do. The main rule against this, basically, or the main rule for this rather, is always have the cell much bigger than the actual object here. So basically, if you don't, it won't work. So that is basically it. That's a good example of spatial partitioning. Okay, so now I'm just going to show you a basic example of implementing a spatial partition when coding. So this is all in C++, and you'll notice that the video is sped up quite a bit just so you don't have to sit around waiting for long. So first of all, we just need to create our basic unit class now. So this is the class for the actual unit itself. Each unit has a position and a pointer to the grid that it lives on. So we make the grid a friend class, as you see there, because a friend class in C++ can access the private and protected members of the class in which it is declared as a friend. So you'll see later when a unit's position changes, it has to adjust with the grid to make sure everything is updated correctly. You're probably wondering why at this point I'm putting a little underscore after the x and the y variable there. It actually doesn't mean anything. It's a rather common naming convention for private member variables, just to keep them separated from methods and public properties. So now that we've created the class for the unit, it's now time to move on to the grid. So as you can see here, as I'm creating the class for the actual grid, I'm going to completely clear it first. So this makes every cell going vertical and horizontal completely null. So to do this, you basically use a double nested for loop. So you can see all the cells that go along the way and up and down the way are completely null. Then once they're set to null, we actually set the number of cells that we actually want. So in this case I'm going to pick 10, and for the actual size I'm going to select 20. So remember when I said before, it's best to make the size of the cell bigger than the actual object, otherwise it won't work at all. And note here that each cell is just a pointer to a unit. So what we'll do next is extend unit with next and previous pointers. So the reason I'm actually doing this is because it lets us organize units into a doubly linked list instead of an array. So each cell in the grid points to the first unit in the list of units within that cell. and each unit has pointers to the units before it and after it in the list. You'll see later in the video why. So now that the grid and the unit classes are complete, the first thing we need to do is actually make sure that the new units are being placed into the grid once they're created. So how we do that is we make the unit class handle this in a constructor, which I'm typing out now. So the method, you can see here, the add method is being defined like so. So dividing by the cell size converts world coordinates to a cell space, and then casting it to an int basically shortens the fractional part so we get the cell index. If you've coded linked lists before, you know that it's always pretty fussy, but the basic idea here is pretty simple. So what we're doing is we find the cell that the unit is currently sitting in, add it to the front of that list, but if there's already a list of units there, we link it in after the new unit. So by this point, what we've done now is basically got the units and placed them in their cells, and in this case, since we're doing soldiers, they're currently hacking away at each other. But like I stated before, not using spatial partitioning does use a lot of resources, which we really don't want to do. So with this new grid, the main method for actually handling the combat looks like this, what I'm typing out now. So what it does, it walks through each cell and then calls the handle cell method on it. And as you can see, what we've done is basically partitioned the battlefield into little tiny skirmishes. So each cell then handles its own combat. As you have a look at this method I'm typing out now, you'll probably notice that it's quite similar to the method for handling combat. So it's comparing each pair of units to see if they're in the same position or not. The only difference here is that we no longer have to compare all of the units in the battle, we just need to compare the units close enough to be in the same cell. And that's basically the entire point of spatial partition, this bit right here. You'll probably also notice as well that we've actually gone from a double nested loop over the units to a triple nested loop over the cells and then the units. So the trick here is that the two inner loops are now over a smaller number of units, which is enough to cancel out the cost of the outer loop over the cells. So we've now solved the performance problem, but what the new problem is now is that the units are stuck in their cells. So if we move a unit past the boundary of the cell that contains it, units in the cell won't see it anymore, but neither will anyone else, so it's kind of pointless. But it's easy to fix. So to fix it, we basically need to do a little work each time a unit moves. So if it crosses a cell's boundary line, we need to remove it from that cell and add it to the new one. So first, we give the unit class a method for changing the position, and that's the method I'm typing out now. So what this bit is doing just now, we're currently seeing which cell the unit was previously in. And these two lines of code I'm about to type out now is basically seeing which cell it's moving to. So what this if statement is doing just now is if the units didn't change cells at all, then we're finished. We can just simply return it. Just looking at it and obviously trying to code it does seem quite complicated, but the basic idea is actually quite straightforward. So the first bit, like I said, checks to see if we've crossed a cell boundary at all. If not, all we need to do is update the unit's position and we're done. However, if the unit has left its current cell, we remove it from that cell's linked list and then add it back to the grid. Like with adding a new unit, that will insert the unit into the linked list for its new cell. This is why we're basically using a double linked list. We can very quickly add and remove units from lists by setting a few pointers. With lots of units moving around each frame, this can be pretty important to do. So everything that you've seen so far works absolutely fine. The only remaining problem that there is that the units only interact when they have the exact same position. So it's absolutely fine if you're playing like the game of chess, but if you're having a more realistic game, that's not really the case. So what we have to do is apply attack distances to take into account. So the pattern still works fine, but instead of just checking for an exact location, we'll do something more like this. So in this problem here, if one unit is within another unit's attack radius, but their center points are in two different cells, we need to split the inner loop out of the handle cell method like we're doing just now. What we're doing just now is just expanding it a little, so what it's doing is also trying the neighboring cells. So the traditional handle unit method calls look for hits between the current unit and the units in 4 of the 8 neighboring cells. If any unit in those neighboring cells is close enough to the edge to be within the unit's attack radius, it will find the hit. But we only look at half the neighbors for the same reason that the inner loop starts after the current unit. It avoids comparing each pair of units twice. So I hope this gives you a better understanding of what spatial partition is, and I hope it helps you actually implement it when you actually come to code it. The whole idea of this and all the code is basically from gamesprogrammingpatterns.com, so go check it out if you want more information. And thanks for watching.